In this video, we are going to prove the Poisson Limit Theorem, which states that a binomial distribution can approximate to a Poisson distribution under certain circumstances that we are going to look at. So let's kick off by reminding what each of the distributions are. So let's start with the binomial distribution. Suppose you are performing an experiment. It could be throwing a coin or maybe tossing a die. Then if you perform, let's say, n trials, n independent trials, then if your goal is to have, let's say, heads, if it's a coin, we are going to denote P the probability of success, which means the probability of obtaining heads. Then the binomial law or the binomial distribution can enable you to calculate the probability that out of the n trials that you are going to perform, that k of them are successes. Okay? And we can write that mathematically as probability that any variable x is equals to k. Okay? You perform n trials, then you want to know the probability that k of those trials are going to be successes. Then you're going to take n combination k, then p to the power k, and 1 minus p to the power n minus k. So this is the binomial law. N is your number of trials, k is the number of successes in those trials, and p is the probability of a success. It's given by the binomial law. What's important to note about this binomial distribution is the mean and the variance. You know, the mean is the expected value or the average value that you can get, okay, if you perform a set of trials or a set of experiments or a set of realizations, if you prefer. So the mean of a binomial distribution, usually denoted mu, is given by NP. So it's just your number of trials times the probability of success. This is also known as the expected value. And the variance, usually denoted sigma squared, where sigma is a standard deviation, is given by NPQ. Okay, where Q here represents the probability of failure. So it's just 1 minus P. Okay, so usually Q here represents a failure, if you want. And it's just 1 minus P, because P and Q are complementary. It's either you have a success or you have a failure. The two should sum up to 1. So this is what we need to know as far as a binomial distribution is concerned. Now, for a Poisson distribution, a Poisson distribution is slightly different. Suppose this time that you are carrying out n independent trials, which means you are carrying a set of realizations, okay? You could be throwing a coin or maybe tossing a die. Then with the Poisson distribution, what interests you here is not the number of trials or the probability of success, but rather a quantity called lambda, which represents the average rate at which events occur in a certain interval, okay, in a certain interval of time. We denote that lambda, so lambda here is just an average rate. So in this case, if you want to calculate the probability, okay, that out of the number of trials that you are performing, let's say you are performing n trials, if you want to calculate probability that k of those trials are going to be positive, then you are going to use the Poisson distribution, which is lambda to the power k e to the negative lambda divided by k factorial. And in this case, you can also calculate the mean. We can show that the mean, mu, in this case, is lambda, as well as the variance. The variance is also lambda. And this lambda is just the average rate of occurrence of the event in question. So with a Poisson distribution, having a knowledge of lambda of this average rate, we are able to really calculate the probability of occurrence of any event. So the Poisson limit theorem then tells us that if n, which means the number of trials, is very large, so if n tends to infinity, then the binomial distribution turns to a Poisson distribution. Mathematically, that means that the limit as n tends to infinity of the binomial distribution n combination k, p to the power k, and 1 minus p to the power n minus k, this turns to e to the minus lambda, lambda to the power k on k factorial. So this is the statement of the Poisson limit theorem. And this is what we are going to show, we are going to prove in the next few minutes. So let me take another paper. So to do this, we are going to make use of a set of approximations. The first is Stirling's formula, or Stirling's approximation, okay, which tells us that the natural logarithm of n factorial, okay, is approximately equal to n natural log of n minus n. So this is Stirling's approximation. We can write this as well in exponential form, okay, as n factorial being approximately equal to exponential n natural log of n minus n. Okay, so both of these are valid. This is just the exponent. If you take the exponential of this expression, you get this. So that's Stirling's approximation. And the second approximation that we are going to use here is just the fact that if you have the natural log, okay, of 1 plus x, okay, then for very small x, this is approximately equal to x. So if you take the Taylor series expansion of ln 1 minus x, if x is very small, then we can neglect higher order terms and just take x, which is the first term. So these are the two approximations that we are going to use to prove the Poisson limit theorem. So let's take our binomial expression. We have n combination k, p to the power k, 1 minus p to the power n minus k. Okay? So if we write this in a more explicit way, we can write the n combination k, that's just n factorial divided by n minus k factorial times k factorial. Then you have p to the power k and 1 minus p to the power n minus k. So we established already that the mean, okay, of the binomial distribution was np, and that the mean of the Poisson distribution is mu. So already we can equate both of these because both means should be the same if you are performing the same experiment. So np should be equal to lambda. So we can write that the expectations are equal. So np, the expectation of the binomial distribution, should be equal to lambda. So already here we can express p as lambda over n. Okay, this was already a first relationship between the binomial and the Poisson. The probability of success expressed as the average occurrence of the event lambda. Then we are going to make use of Stirling's approximation to write the expression of n factorial and n minus k factorial. So this expression this whole expression becomes, I'll write it down here, n factorial. We're just going to write it as exponential n ln n minus n. So that's the expression of n factorial. Then divided by n minus k factorial, which is, we just replace n by n minus k, so that's e to the n minus k times ln of n minus k minus n minus k. Okay, so I've just replaced n by n minus k, and then we have k factorial here, multiplied by p, which is lambda over n to the power k. We replace p here, and here we are having 1 minus lambda over n to the n minus k. Okay, hope that's clear. So we can combine all of these, okay, as one exponential. We're going to have exponential, okay, let me just put a big bracket here. We are going to have n ln n minus n, then minus all of these, so minus n minus k ln n minus k, okay, and then minus minus, so that's a plus n minus k. Hope you can see that. And then we close this bracket, times 1 over k factorial, and then this expression, lambda over n to the power k, and this expression, 1 minus lambda over n to the power n minus k. Okay, then we are going to try to simplify this expression. So we are going to make use of the second approximation to have a simplified expression of this natural logarithm. And the way we do that, n ln n minus n minus n minus k. Okay, so the way we do that is that we are going to factor out n from this logarithm. So that's going to give us ln of n, okay, plus ln of 1 minus k on n. And then we close this bracket, plus n minus k. And this closed, we have 1 over k factorial here, lambda over n to the power k, 1 minus lambda over n to the power n minus k. So what I have done here, I have simply factored out n, so I can write that in a more explicit way up here. So natural log of n minus k is just natural log of n times 1 minus k on n. And then we use the identity of the log of a product. The log of a product is just the sum of logs. So this gives us the sum of these two logarithms. And that's what I have just written here. Hope that's clear. And then we recognize that this expression, ln of 1 minus k over n, okay, since n is very large, k over n is very small, so this whole expression is just negative k over n. It approximates to negative k over n, following this, this approximation. So we then have a simplified expression. We are going to have e to the n ln n minus n minus k, okay, times ln n minus k over n, and then plus n minus k. And we close this, and then we have the constant beside. Hope everything is clear up to this point. Then we notice that this exponential can be simplified. We are going to have terms that are very common, so we can expand these and simplify terms. We're going to have e to the n ln n minus n. Okay, let's expand this. We're going to have negative n ln n, the first term, then the second term, plus k ln n, That's the second term. And then we do the same thing here. We're going to have plus k, this multiplied by this, and then this multiplied by that. We are going to have minus k squared over n. And then we have this constant here, 1 over k factorial, lambda over n to the power k, 1 minus lambda over n to the power n minus k. And then we can notice that there are terms that are going to cancel. This term cancels with this one. Okay, just notice that I forgot to put, there's this n minus k that I omitted here. So here we should have plus n minus k before parenthesis closed. Okay, so ln n cancels with this. We have n that cancels here. We have k that cancels also here. And we are left just with this term and this term. Okay, so I'm going to take another page to write that. So we are going to be left with e to the power k ln n and then minus k squared over n. So k ln n minus k squared over n. That's all that exponential. All this exponential simplifies to this one. And then we attach the constants. Beside, we have 1 over k factorial, lambda over n to the power k, and 1 minus lambda over n to the power n minus k. Okay, so here we have an expression that looks really good. So let's simplify this. We can write that as, let me just write this constant before. We're going to have 1 over k factorial, then lambda to the power k over n to the power k, okay, this term, then e to the k ln n, that's just n to the power k, hope you can see that, the exponential, then e to the negative k over n squared, that's just e to the negative k squared over n, and then we have this 1 minus lambda over n to the power n minus k. Okay, so you can notice that this term is going to cancel here. Okay, and this term for very large n, it's going to turn to 0. Okay, this term turns to 0 for very large n, and e to the power 0 turns to 1. So this whole term is approximately 1 in the limit of large n. Then we are going to get 1 over k factorial, lambda to the power k, okay, times 1 minus lambda over n to the power n minus k. Hope that's clear. So we are almost getting there, and we need to do one last approximation, which is on this term. So we can write this expression. Okay, let me just do that on the side. 1 minus lambda over n to the power n minus k can be written as exponential, okay, and then logarithm of all of these, so n minus k times natural log of 1 minus lambda over n. Hope you can see that. So it's exponential to the power log of all of this expression, and then I can bring this on the back. So that's just the law of logarithm. And then here we can again make use of our approximation that we have at the beginning. Recall that for small x, log of 1 plus x is approximately equals to x. So when n is very large, log of 1 minus lambda over n is very large, is very small. So this approximates to negative lambda over n, which means that all this expression becomes e to the power n minus k times negative lambda over n. And we can simplify this as e to the power that's minus lambda, okay, and then plus k lambda over n. Hope you're seeing that. And then here we can make again another approximation, okay, which is that as n tends to infinity, then e to the negative lambda plus k lambda over n would return to e to the negative lambda, okay, because this turns to 0, in other words. So for large n, this turns to 0, and e to the negative lambda turns to, and e to the negative lambda base turns to that. So we can take this expression and plug it here. So for large n, we have that our binomial law, so the expression we had at the beginning, 1 minus p to the power n minus k, okay, this turns to 1 over k factorial, lambda to the power k, and this, which is e to the negative lambda. And this is just the expression of the Poisson distribution. So we arrive at the conclusion that the binomial turns to a Poisson distribution in the limit n tends towards infinity. Okay, hope that's clear. If you have any questions or remarks, feel free to point them in the comments, and I see you in the next video.